and welcome to the first of 3 lessons this week on reciprocal trig functions. From the learning pack, you should be aware of what these reciprocal trig functions are. You should have some experience of sketching the graphs, and what we'll do in the first lesson is we'll take that knowledge and extend it to solving some basic equations. So reciprocal trig functions are sec, cosec, and cot. And what you saw in the learning pack is that sec theta is 1 over cos theta. You saw that cosec theta is 1 over sine theta. And you saw that cot theta was 1 over tan theta. Now we use these relationships to sketch these graphs. So rather than sketch them from scratch, it makes more sense if I show you them from Desmos, but I'll explain how I would sketch it when asked. So this one here, we've got the graph in blue of y equals cos theta. In red, we have the graph y equals sec theta. And if I had been asked to draw the graph of y equals sec theta, I'd start off by sketching y equals cos theta. The reason being, it's going to be easy for me now to take a reciprocal. So all I'm going to do is find the value of cos theta at certain key x points, and I'm going to do 1 over the y value. So where x is 0, cos theta is 1. So therefore sec theta will be 1 over 1, which is 1, which is where these two graphs meet. Another example would be where cos theta, theta is 60 degrees right here. So theta is 60 degrees. Cos theta is a half. Sec theta then would be 1 divided by a half, which is 2. That allows us to plot that point. The next real key value, though, is coming from where cos theta equals 0. So when theta is equal to 90, what we have, just changing my pen, when theta equals 90, cos graph goes through 0, and if we did 1 divided by 0, we have an undefined answer. And so that gives us an asymptote in the sec graph. So we can use all that information and the fact that these graphs have the repeating patterns to draw the complete graph of sec theta between minus 540 and 540. So the graph of cosec theta is identical. What we have then is start off with your sketch of y equals sine theta. You then take the reciprocal of some key values, and that becomes your graph of cosec theta. And again, you can see the principles here. Wherever sine theta reaches as high as 1, cosec theta will also be 1. Wherever sine theta goes through 0, you have a vertical asymptote, because 1 divided by 0 is undefined. Let me just draw that asymptote in again here. So that would be the asymptote. All right, similar process, and you can see that the graph of sec theta and cosec theta are related in the same way as the graphs of sine theta and cos theta. The next one then, the tan graph, which traditionally poses a little bit more of a problem, just because it has slightly different patterns than the other two. In blue, I've got y equals tan theta, and then in red, I've got y equals cot theta. Now, the tan graph, if you look here in the blue, goes through 0, 0, and then 180 degrees later it goes through 0, 0, and 180 degrees later it goes through 0, 0. Now, using the same logic as previously, wherever the tan graph here goes through 0, it means that the cot graph will have an asymptote, a vertical asymptote. So the asymptotes are at 0, 180, 360, and so on. And then we just use the principle that wherever the tan graph has an asymptote, which is at 90 degrees, and every 180 after 90 degrees, we're going to have a 0 value. And that's it. That's how you go about sketching those 3 graphs. So the second question from the prep work review asks you to do a little bit of thinking based on that knowledge. Sketch on the same set of axes in the interval 0 to 360 the graphs of y equals cot theta and y equals sine 2 theta. Now the cot theta graph we've just gone through, start with your tan theta graph and then do 1 over, and then you get your cot theta graph. Sine 2 theta is a transformation of the original sine theta graph. Okay? it has been affected by a horizontal stretch in the x direction by a scale factor of 1/2, which means that the sine graph that we're interested in no longer exists only between 0 and 360. Okay, well, I should say ordinarily between 0 and 360, the sine graph has a period of 1, i.e. 1 up, down, and back up again, 1 cycle. But this time we have 2 cycles of the graph between 0 and 360. So actually, we've increased its frequency. So how many solutions are there to this equation? Well, we've got 1, 2, 3, 4, 5, and 6. It's just wherever those 2 graphs intersect. Now, because we've got an accurate graph, we can actually write down what the solutions actually would be. Okay, so we have our first intersection over there at 45 degrees. I know we're not asked to do this in the question, but we can, since we can see it from the graph. Theta is 45 degrees. The next solution at theta is 90 degrees. The next solution over here is at theta is 135 degrees. The next solution up here at 225 degrees. The second to last solution over here at 270 degrees. And then the final solution over here at 315 degrees. So now we get into some simplifications, and this is really important to get these simplifications and become confident with them, because that will allow you to access the more difficult proofs that we're going to look at later in the week. So we're going to use the definitions of sec, cosec, cot, and tan to help us. So it's worth writing these down. Sec theta is 1 over cos theta. Cosec theta is 1 over sine theta. Cot theta is 1 over tan theta, and then we know that tan theta is sine theta over cos theta. Okay, all of this we know. We're going to look at this one a bit more detail, because actually, if we're doing 1 over tan, and tan is sine over cos, so say we did 1 divided by sine over cos, you actually get cos theta over sine theta, which is a very important one to know as well, and to be confident, as you'll see in a second. So now that we've written all of our definitions out as a reference, let's get into the question. So the first one says, simplify sine theta multiplied by cot theta. So what we do here is we just switch out anything that we can. So we can switch out cot theta as 1 over tan theta. We still have a problem that we can't really simplify sine and tan together. Nothing cancels out, which is what we're looking for. So we'll go one stage further, and we'll say that cot theta is actually cos theta over sine theta. And now we can start to see what we can cancel out, because if you have sine theta multiplied by cos theta divided by sine theta, you just have cos theta. And that's our simplification. So for part B, we have tan theta cot theta. A little bit simpler, this one. So we'll switch out the cot theta because it's the only thing we can do. And we just end up with tan theta multiplied by 1 over tan theta, which just shrinks down to 1. And it's important to remember that these are actually identities. This is true for any value of theta. For C, we've got tan 2 theta multiplied by cosec 2 theta. So let's switch out anything that we can. All right, so firstly I'm going to do tan 2 theta, then multiplied by 1 over sine 2 theta. Okay, the 2 thetas aren't causing us a problem. We're just thinking of 2 theta almost like another variable, x, and applying our identities as we can. Now tan and sine, we have the same problem as before. They don't really cancel. So I could write tan as sine 2 theta over cos 2 theta, and then I can multiply by 1 over sine 2 theta. So sine 2 theta multiplied by 1 divided by cos 2 theta multiplied by sine 2 theta, quite a mouthful there. The sines cancel, and so we end up with 1 over cos 2 theta, which ultimately we can write as sec 2 theta. And then part D, we have this slightly more tricky looking one, but we've got cos theta sine theta multiplied by cot theta plus tan theta. Now, you'll see this a lot when you're doing proofs, but if you've got a bracket like this, it does make sense to expand the bracket. And that's what we're going to do, just not yet. So I'm going to rewrite this using what I know about cot theta and tan theta. So cos theta sine theta part stays the same, open bracket. Now, because I'm going to be simplifying using this cos theta sine theta, it makes sense to write both cot and tan in terms of sine and cos. So we'll go to here, cot theta is cos theta over sine theta, and tan theta is sine theta over cos theta. So now the whole thing is in terms of cos and sine, and it's going to make life a little bit easier. So the next thing I'm going to do is simplify this bracket. I'm going to try and combine these into a single fraction. So my single fraction would have the common denominator, sine theta cos theta. Okay, when we do algebraic fractions and the like, we multiply the denominators together in order to give us our common denominator. But we have to multiply the numerators accordingly. So if we multiply sine theta by cos theta, we have to multiply cos theta by cos theta, giving us cos squared theta. If we multiply this cos theta by sine theta to get the common denominator, we must multiply sine theta by sine theta. And then it's being divided by sine theta cos theta. Okay, let's just combine these two fractions algebraically together. Now we know, and we should be very familiar with at this point, that cos theta plus sine theta is 1. Which shrinks that bracket down nicely. And if you multiply this by this fraction, you just end up with the 1. Now we'll do a lot more work on simplifications and proofs in our third lesson this week. But for the final thing, and for the new learning, I suppose, part of this lesson, we're going to look at some trig equations. So I have 3 examples of trig equations that I want to work through, and then it's over to you to do some practice. So solving each of these trigonometric equations, okay, we've got sec all of a sudden. All right, now let's have a look and see how that actually affects what it is we're trying to do. So I start with 2 sec theta equals 3. I'll start by rearranging the equation to have sec theta equals 3 over 2. Now I'm just remembering that sec theta is 1 over cos theta. We never solve equations leaving them as sec, cosec, or cot. We turn them into cos, sine, cos, and tan. So here we have 1 over cos theta is going to be 3 over 2, which means that cos theta is 2 over 3. All we're doing is taking the reciprocal of the fraction because we're using this reciprocal trig function. So let's go ahead and solve it as we know how to do. Make sure you calculate this in degrees. We'll do arc cos of 2/3. So theta comes out as 48.2 degrees. And then from the symmetry in the graph, we know that we do 360 minus this, and we have 312 degrees, both the 3 significant figures. And those are our 2 solutions between 0 and 360. So you can see that once you've got this as a cos theta, use the same techniques that you've learned already. This is just the added layer. Okay? It's the added part that you need to do now that we understand sec, cosec, and cot. So for this one, we're going to do the same thing. We're going to firstly divide both sides by 2. And then we're going to, pardon me, someone's coming in. Okay. Yeah, so what we're going to do here then is we're going to again use this idea of a reciprocal. So we know that tan of x minus 30, because tan is what's cot is related to, it's 1 over tan. So we're just going to then use the reciprocal of that fraction, tan of x minus 30 equals 2/3. And we're going to solve our equation. So we use arc tan of 2/3 this time. Now we're going to remember that our limits are being affected by this bracket. So this linear function of x here, we need to apply that linear function to the limits. So the limits are actually going to be minus 30, x minus 30 to 330. Okay, those are our new limits for this equation. So therefore, our x minus 30 comes out as whatever we get from the calculator here. So we'll do arctan 2/3, which is 33.7 degrees. And we know that this repeats every 180 degrees, so we'll add 180 to that, and we get 214 degrees, again, both two significant figures. If we added another 180, then we'd be beyond our limits. So these are the only ones that are in our limits. Equally, if we took 180 away from 33.7, we'd also find the same thing. So our x then just becomes 63.7 degrees and 244 degrees, again, all rounded to the three significant figures. So the only additional part is the cot. Okay? Everything else is the same. If cot of this equals 3/2, then tan of this is equal to 2/3. So for our final one here, again, we've got a bracket, and we're going to have to multiply that bracket out. But first, we'll do a little bit of work. So we've got cosec y, which is 1/sine y minus that sine y, multiplied by sec squared y equals 2. Okay, so I've just replaced cosec with 1/sine. I'm going to combine these two things together. So turning sine y into a fraction over sine y becomes 1 minus sine squared y divided by sine y. Hopefully you can see that. To turn this into a fraction where the denominator is sine y, we have to multiply this by sine y. So we then got sec squared y. We'll carry on down. We know that 1 minus sine squared y is cos squared y. So we have cos squared y divided by sine y multiplied by, might be a good idea now to write this sec squared as 1/cos squared y. And you can see how things are cancelling down quite nicely. Cos squared y multiplied by 1/cos squared y. These cancel each other out. So we end up with 1/sine y is 2. So therefore sine y equals 1/2. So when sine y equals 1/2, y is going to be arc sine of this 1/2. So y comes out as radians this question. Yeah. So we've got pi by 6. And then using the symmetry in the graph, we've also got pi by 6. So there we have it. Those are the prep work review questions, plus the 3 examples that we're going to be working through in class. Post any questions that you have in the general chat. Thanks, everybody.